couple quick announcements. Logistics stuff that keeps getting more kind of annoying, but first thing is that the final time slot. There was a post on Piazza about this, and I've actually been waiting on this until sending out the information about everything. It is actually not scheduled yet, the final time, because we don't have an actual final. We have a presentation sessions that do different scheduling for that. I'm hoping that will be done today, and I will make a post on Piazza about that. The presentations are going to be in 2 weeks still, but that's, as I said, the idea there is it's just 1 or 2 slides, but we'll post more about that in a second. The time for the final, though, that is coming imminently. It's just going to be a poster presentation. You don't have to do, not going to be a final exam, but it will be coming soon. The other thing is that the homework 4 is posted now. So you can check that out. It's also going to be due in 2 weeks. That happens to be the same day as the presentations. Those are pretty short, so hopefully it won't cause too much difficulty. Sorry that we took an extra day coming out. The other thing is the auto lab, the homework's there. The auto lab grader for the programming parts isn't there yet. We'll get that out in the next day or two, and hopefully that's all taken care of soon. Are there any questions about kind of the? I think there were a few Piazza posts. Were there any questions about the exam or final presentation? Not exam. Final presentation or project that I did not answer or ask on.
Project feedback yet. Should we be worried about that? Or?
So you should have gotten one for the first one, right? The milestone. So that's a little odd. I mean, you shouldn't be worried about it. That's odd. I don't know why that would happen. Did anyone else not get feedback for the first?
For the milestone?
No, for the milestone, yeah, that's still waiting. But for the original one, everyone else. So your portion of the week, I guess, isn't it? I'll look into that. I'm not sure what happened. I'll just look at the milestone, I guess. Anything else?
When was the fourth homework posted?
Just right now, just today. Yeah. It's up now and it's due in 2 weeks. So we're pushing the deadline for that back by 2 days because we're late getting it out 2 days.
So I also want to add that since the problem set is out a little bit late, do post things to Piazza and we'll try to be very responsive on that in order to, but you still have the full 2 weeks to complete it in.
Yeah. Just unfortunately overlapped with a presentation now, but it's about to give you the extra 2 days. Okay?
Okay. Okay, great. Get started. So today we're going to, I'm going to introduce natural language processing, and I'm basically going to give you sort of a very high level touching on several of the challenges in natural language processing, define what it is and what are some of the challenges of it. And then at the second part of it will be to talk about one particular method called engrams. All right. Natural language processing is, here's the outline for, like I said, we're going to talk about. We'll spend a little bit of time about what is the natural language processing, and then we'll talk about these challenges and tasks that have been segmented off that need to be achieved in order to sort of attack the NLP problem as a whole. And then talk a little bit about some of the applications that you might, or additional tasks that you might do with these techniques, and talk about how probability and learning has come into play. It wasn't part of the original conception of natural language processing, but now has become very powerful instruments within it. And give a little bit of the history at the very end, just to give you some notion of where it started and where it's going. And we can talk a little bit in this as we get into this, and there's a couple slides about this, about sort of a challenge that you have in general in AI, but we haven't really discussed much in here. In fact, we don't discuss much in here, is that are doing things the way that humans do it, is that necessarily the right way to do it in terms, or is the end justify the means? Meaning that we don't have to do it the way it seems intuitive to us, as long as we get the right results. All right, and so that's kind of a constant challenge in AI. All right, so let's go into it. Let's just delve into it. So we'll start in what is NLP. So NLP, or natural language processing, is the branch of computer science that's focused on having computers communicate with people through language. All right? So, as you can imagine, this includes written words. It also includes spoken words. It includes different languages. So lots of different ways we do it. And as you can imagine, this is not just the study of computer science. This is also the study of lots of different fields. In particular, one is computational linguistics. Lots of different ways to understand how humans understand language, how machines can understand language, and hopefully we can see synergies between those two studies. So as I said, there's lots of different fields that look at this. Artificial intelligence for here, but formal language automata theory, machine learning, people learn this, and we'll see how the machine learning has come into play with the artificial intelligence, not that they're separate communities. Linguists, computational linguists. Often, I got my PhD at UMass, and the very strong NLP component there was handled by, at that time, eons ago, by Wendy Leonard. But one of the powerful linguists at the time there was also part of the linguistic department at UMass, which is Barbara Foster. And they used to work very closely together. Cognitive science. You see this all the times, in particular at the University of Pennsylvania. They have a cognitive science program there, and they have a collection of both NLP people, Arvind Joshi, Bonnie Weber, and they're also the cognitive scientists that all work together, all focusing on the same idea of how to understand language. What does it mean to convey, both in between humans and also for epistemology, about understanding how language means knowledge, and also for how computers and people might interact. They all sort of attack the same issue from different points. Philosophy of language, anybody's familiar. There's lots of, dating back to, before Frege and Wittgenstein, and more modern ones like Kripke. These are all different ways of doing this, encoding and analysis of language, and trying to understand what reference means, understanding the epistemology about how you convey knowledge. So these are all these kind of interesting different fields, basically trying to attack the same problem. Okay, but with maybe different goals, but very similar kind of issues that you're trying to explore. So, what is it what we're looking at for the communication? What does it mean? So for this particular slide of it, let's just look at what language might be used for. The ideal here is the goal is in the production and the comprehension of the natural language is what we're going to call communication. So starting from the speaker, let's just go through like a little scenario from here. Starting from the speaker may have some intention to say something, have some thoughts, may not be articulated in a particular language except for the quote-unquote language of thought, if such a thing exists. And then you have to convert that, whatever that thought is that you want to do, into something that can be communicated. So into a string of words that then can be communicated, for example, or a string of things that are said. And that's sort of what they call tactical generation. And then you take the synthesis, which outputs the string in the desired modality, text or speech. Actually take it from here and then convey it to another person. Now on the flip side, somebody else has to hear about it. Right? Somebody has to hear it and understand it. And understand in order for that communication to take effect. So what do they have to do? They have to map that input from whatever was set output from, and bring it into something that they can work on. So in the case, an example here is like optical character recognition or speech recognition. We see these characters, we see these marks on a page, and we're trying to understand whether they represent particular letters in the case of OCR. So then the analysis here is then to determine if the information content of the string, syntactic interpretation, parsing, find the correct parse tree that shows the phrase structure of the string. So if you had a sentence, you might be doing, you guys probably never did sentence diagramming in your time, but that was something I did back, you did, whoa. Okay, I stand corrected. Well, as you remember, you would pick things out for like noun phrases, you come out with these sort of context-free grammars, and you'd break apart the sentence into different pieces, and you'd match up certain words based on different ways you would parse it. So there you'd have your syntactic operations where you match up, say something's a determiner, something's a noun, something's a verb, something's a prepositional phrase. And then you're going to go from the syntactic stream into some kind of semantic interpretation, which is often a very, very difficult step. And the idea here is to take this parse tree that you did from the syntactic piece and then map that into literal meanings of the words. Here are the words that it's going to mean. And then finally, and this is something that's really difficult, is this pragmatic interpretation, which is that given the words, just because you have the words doesn't mean that you know what the meaning of those words are unless you have a greater context. And the pragmatics will allow you to sort of assign particular understanding of what words they might be. If you see a word like plant, is it a factory? Is it a something that a botanical something that grows? You don't know what to assign to it, and you need sometimes context to be able to determine that. All right, and then the incorporation here is simply something that you say, all right, do I believe this or not? Does the listener believe this? If they do believe this, if it were a computer that had this notion of believe, then it would be stored into its database of facts or beliefs. All right. So a really simple example here is this notion of in the Wumpus world is you have this intention. The speaker has this intention to say the Wumpus is dead. All right. I don't know if you guys remember the game Wumpus or not, but so the Wumpus is dead. So, and in this case, the way that they choose the modality in which they way to say it is they say the Wumpus is dead, right? And then so you're going to try to take that perception in here, and you're going to then try to do some kind of converting it into words, parsing it, trying to understand the semantic interpretation of it, the pragmatic interpretation, and then understand once you disambiguate that you got this logical expression here. Now, again, this is a function that we would use in the computers. I'm not sure. There's a big debate about whether we actually have these kind of logical precepts in our thoughts. And then you say, this, yes, this is true, yes. Then I'm going to tell the knowledge base that I'm going to incorporate what was just communicated to me from the speaker. All right? So that's a great thing if you could do that. Okay, that's a great thing to do, be able to do that. And you can imagine in robotics, where you want to have robotics interaction with human beings, this ability to interact with speech is a critical factor to its adoption. Right? All right. So what are some of the steps that you have to do and have to be concerned with? Well, as I said, we have things that we have to worry about: the syntax, we have to worry about the semantics, and we have to worry about the pragmatics. So focusing on syntax, syntax is concerned with the proper ordering of the words and its effect on meaning. So you have the dog bit the boy bit the dog, bit boy dog the. That doesn't have any meaning, right? So you're trying to do a parsing that makes sense and that you can assign particular parts of speech to it. Color is a clean idea, sleep furiously, which is a famous NLP phrase that they love to use, is something that has no meaning in a sense, but it syntactically is absolutely correct, right? So then you go to semantics, which is another step, which is the meaning of the words and phrases. And as I said before, if you see the word plant as you got it from the syntactic analysis, a plant may be a photosynthetic organism, a plant may be a manufacturing facility, and a plant may be an act of sowing. So here you're trying to assign which kind of plant you're using here, and you're trying to assign the appropriate meanings. And then pragmatic concerns the overall communication and social context and its effect on interpretation. So you see this: the ham sandwich wants another beer, right? I mean, how do you parse that? How do you make sense of that? I mean, I remember, so the idea here is, you know, that there's somebody out there who's ordered a ham sandwich, right? And the waitress is saying, hey, the ham sandwich wants another beer, but you don't know that by looking at this, right? I mean, so you'd have to know the context that you're inside of a restaurant, that there's orders, and there's people who are doing these things. That's the praxis that you're trying to do underneath it. John thinks, and so this is a co-reference. John thinks in vanilla, okay? You don't know what that vanilla means. You don't know the context of that, but it might make perfect sense if you were cooking or think, you know, and then someone had asked them, what do you think we should use, ginger or this? And they said, no, John thinks vanilla. It makes perfect sense. But you don't know it outside of the context, right? Here, you look at these sentences without any kind of context, and you have no idea what they really mean. Right? Okay. So let's look at some of this kind of a modular way of trying to understand this. This is one strategy that you might use. So you have these kind of sound waves that come in. We have this acoustic phonetic models that are going to then change them into words. Words, and then we're going to take the syntax and we're going to make them into these parse trees to assign different parts of speech to it. And then we're going to assign semantics to it. And then we're going to do the literal meaning. And we're going to look at the pragmatics to get the context in order to get the meaning of these kind of weird phrases like ham sandwich. And we're going to get the meaning, okay? Whoops. So, I don't know if you're here. I'm looking at this and I'm thinking, okay, doable, this is looking pretty hard, this is looking way hard, right? So, and this is only suggesting a control model, which is that we're always going this direction. As we'll see a little bit later in the lecture, always going in this direction has its own problems because we're stovepiping, right? We're doing it in a particular set of orders, and some resolution may require input from other pieces here. It's hard to believe that you don't have to go back and around to have to redo syntactic bindings based on some semantics that you've done from analysis. Okay? So, all right, so one of the things that makes NLP really, really hard is ambiguity. And ambiguity shows up in lots of different forms, okay? So let's look at some of the forms of ambiguity. Natural language is highly ambiguous and must be disambiguated. Before I came into computer science, which I did not originate in, I had never thought of or heard of the word disambiguate. So disambiguate means basically to get rid of the ambiguity. So take a look at this. I saw the man on the hill with a telescope. So does that mean I saw the man who was standing on the hill with a telescope? Or did I see the man who's on the hill and I saw it with a telescope? Right? There are multiple different parsings to this. Similar here, I saw the Grand Canyon flying to LA. So one meaning is obviously pretty preposterous, but still you can imagine this, all right? I won't even go into it. Here's another favorite of the NLP environment. Time flies like an arrow. And I think there are like 4 parsers to this. I'm not going to try to go through and reconstruct them because every time I do, I never quite get them. But the idea is that time flies can also be a particular special kind of fly. You know, time flies, like fruit flies. So there are time flies. So time flies like an arrow. You know, time flies like an arrow. And, you know, I can go through them. But again, you can imagine these kind of parsings. And we as humans have a hard time understanding them without context. Same thing here, horse flies like sugar cubes, time runners like a coach, time runners like a coach, time runners like a coach. So lots of different meanings here, right? Lots of different meanings. Time cars like a Porsche. So all these things are ambiguous in their meaning. And by themselves, even as humans, we have a hard time with them. But some of them we would give natural meanings to, right? I saw the man on the hill with a telescope. I would tend to believe that it was me that had the telescope, right? That I had the telescope, and I saw the man through my telescope. But maybe not. Maybe other people have different intentions. But that's going to get to a sense of what we're going to come up to. It's foreshadowing is that there are different probabilities of probable interpretations to things and values, and so probabilities are going to play a great part into this. Okay, so more notions of ambiguity. It is ubiquitous. So here in a speech understanding system, you can say recognize speech versus recognize beach, right? And if I said that both fast, and especially the way I mumble, they would both sound the same. Also, youth in Asia, or euthanasia, 2 things you do not want to confuse, right? Again, ambiguity, all right? Syntactic analysis. I ate spaghetti with chopsticks versus I ate spaghetti with meatballs. So notice that here, the with is describing how ate, right? I ate with chopsticks here. Where over here, it's describing something that's with the spaghetti. So you have different kind of bindings that you're making here. Different kinds of use of the semantic analysis. The dog is in the pen versus the ink is in the pen. 2 different pens, right? One is a fenced-in area, and the other one is something you write with. I put the plant in the window versus Ford put the plant in Mexico. Again, 2 different notions of the word plant. Pragmatic analysis, I think this is a great example here. This is from the Pink Panther Strikes Again. So Clouseau says, does your dog bite? And the hotel clerk says, no. And Clouseau says, nice doggy. And the dog barks and bites Clouseau in the hand. Clouseau says, I thought you said your dog did not bite. And the hotel clerk says, that is not my dog. Okay, so again, this is all the sense of this kind of context, this in the sense of how the context determines the meaning of these things, okay? Okay, one of the things about ambiguity is that it is explosive. It can happen, and one of the great ways of adding to that is this notion of adding prepositional phrases to things. So in an English sentence that's ending in n prepositional phrases has over to the n syntactic interpretations. So I saw the man with a telescope has 2 parses. I saw the man on the hill with a telescope has 5 parses. I saw the man on the hill in Texas with a telescope has 14 parses. And I saw the man on the hill in Texas with a telescope at noon has 42 parses. So you can see how this can explode on you, basically, with this kind of different ambiguities, just with adding prepositional phrases. Okay, and finally, I saw the man on the hill in Texas with a telescope at noon on Monday, 132 parses. Okay? Okay, so just quickly again, often humor is a play on this kind of ambiguity. Many jokes rely on this kind of ambiguity. Just a couple of these things we can go through. We don't have to go through them all. It's like Groucho Marx. One morning I shot an elephant in my pajamas. How he got into my pajamas, I'll never know, right? She criticized my apartment, so I knocked her flat. Even I had to look at that twice, too, you know, and I was like, what? But of course, flat means her apartment. Noah took all the animals on the ark in pairs, except the worms. They came in apples. Policeman to little boy, we are looking for a thief with a bicycle. Little boy, wouldn't you be better using your eyes? And finally, why is the teacher wearing sunglasses? Because the class is so bright. Right, so we're playing on what bright might be. Okay, so why is language ambiguous? Well, having a unique linguistic expression for every possible conceptualization that could be conveyed would make language overly complex, right? If we had to be absolutely explicit about every particular thing to delimit it from everything like that, we would never communicate. We would be still starting our first sentence, you know, since we were born, basically. So we rely on there being ways to disambiguate based on context, common ideas, common social customs, all these kind of things. And for the most part, it works. We're able to use fairly approximate sentences, you know, but we're able to communicate and get our ideas across. And there are times when it doesn't quite work, and usually it's on the most critical ideas, but that's what happens. We're still able to communicate fairly well without being 100% specific. All right, so ambiguity is the primary differences between natural and computer language. In programs, right, we have very specific, definitive meanings for each of those things. They're well known. They have there's no ambiguity in those expressions. There are rules that rule out either precedence or ordering or formats. So there's no question about it. There's no ambiguity into what these expressions mean. Here in our language, there is that kind of ambiguity, and when we're doing natural language processing, we have to handle that ambiguity. Okay, so moving on from this, processing naturally involves many varied syntactic, semantic, and pragmatic tasks in addition to other problems. So now let's focus on what those problems are. As we saw in that stovepiping where we had syntactic tasks, semantic tasks, and pragmatics tasks or discourse tasks, let's look at each one of them separately for the moment and what those tasks involve. So syntactic tasks might be, first one would be word segmentation. And here we have to break out a string of characters, graphemes, into a sequence of words. So somehow we have to break it out, and given this set of text or words, we have to break them into our speech. We have to break it into individual words. In some written languages, in Chinese, words are not separated by spaces. All right. Even in English, characters other than white space can be used to separate words. There's punctuation and various things. And here are some examples where it gets problematic when you're trying to break things up. So here, you can imagine jumping the shark.com, MySpace, Plucker's Winger. This would probably not be a good breakdown of this words because it's probably not Plucker's. I mean, this would be all right, Plucker's wing bar, but Plucker's swing bar, it's probably more likely a wing bar than a swing bar. So, but you can see that it's hard to break those down. All right. Morphology analysis. And the idea here is that morphology is the field of linguistics that studies the internal structure of the words. You try to find morpheme, which is the smallest unit of meaning, linguistic unit that has semantic meaning. So it could be just little pieces of it, carry, pre, ed, suffixes and prefixes, things that have particular little pieces of meaning here. So you can imagine breaking down words that are converted here into things like carried and breaking down to carry, and ed, which is going to make it a past tense. Independent in, and then dependently. Same thing with Google. All these ways are sort of getting the roots and getting the other pieces, the meaning. Here's an interesting one because you don't know really what this word means if you think about it. All right, is if it's unlockable, right? The idea here is that you can't lock it, right? And unlockable means you can't unlock it, right? So it's a funny word in that sense, all right? Okay, so another syntactic task is to do parts of speech tagging, or POS tagging. And the idea here is, again, to try to assign, as you parse these sentences out, try to assign the syntactic classes to the each word. So this is like a pronoun, a verb, a determiner, a noun, a preposition, and a noun. So again, you go through a process which we're not going to talk a lot about in this lecture, which is parsing, in order to create this parse tree, in order to assign these parts of speeches and tag the words. Same thing right down here, pronoun, a verb, the determiner, noun, saw, a conjunction, a verb, a participle, the verb, the pronoun, preposition, the determiner, and the noun. And you can see that if you look at each word, you wouldn't know that, for example, to is a participle here, right? So useful for subsequent syntactic parsing and word sense disambiguation. It's sort of like once you have it all parsed out, this helps inform the semantic in particular phase, all right? Phrase chunking, again, this is when it's another kind of parsing task. This is when you find all the non-recursive noun phrases and verb phrases in a sentence, and you break it down to the non-decomposable. So you have a noun phrase for I, a verb phrase for ate, and this noun phrase, the spaghetti, prepositional phrase with, a noun phrase, meatballs. So again, you're parsing these things down into these chunks that then inform the semantic and sometimes the pragmatics too, phases. Okay, so here's just a simple parse tree. Again, I'm not showing you how to do this, where if you have this kind of grammar where a sentence is made up of a noun phrase and a verb phrase, and then the noun phrases can have a form, in this particular case, a pronoun, but there could be other ones depending on how you're parsing it. And then you're matching all this grammar, basically, to the sentence. And that's how you can do this kind of parts of speech assignment. Again, as you take this grammar up here, and then using parsing, you assign the grammar to the sentences. Again, I'm not telling you how to do that yet. Okay? Okay. So now that's the syntactic tasks. Now let's look at the semantic tasks. So semantic tasks, one of them is word sense disambiguation. And here we have words in natural language usually have a fair number of different possible meanings. Ellen has a strong interest in computational linguistics. Ellen pays a large amount of interest in her credit card. Clearly, those are two forms of interest. For many tasks, question, answering, translation, you know the proper meaning of those words, right? So if you're doing machine translation, right, from English to Spanish, for example, you obviously need to make sure you use the right word there. Semantic role labeling, this is something you see frequently again, where you're trying to sort of assign roles. You're now giving some structure and meaning to the sentence by assigning roles to different words that you see there. So you can almost think of it as a little bit like a template. You can imagine that you have an agent who's going to do something and has some source and some destination, and you're trying to find those roles in the utterance or the language that you got in front of you. All right? So in doing that, you can imagine, for example, here we have these roles: agent, patient, source, destination, instrument. And if you see, here's the sentence in front of you. John drove Mary from Austin to Dallas in his Toyota Prius. And so John is the agent. Mary, this is what the action of the semantic role labeling is doing, is you're trying to assign, oh, John is an agent, Mary's the patient, Austin is the source, the destination is the Dallas, and how did they do that? They did it in the Prius. Okay? Here, the hammer broke the window. And notice here, the hammer is not listed as the agent here. The hammer is the instrument that broke the window, and the window is the patient, which is really just the end effect. And the reason this becomes this way is that there are usually some kind of outside rules that are helping you govern these things. For example, one rule might be agent has to be human. So therefore, that rules out that a hammer could be the agent. So then it becomes something else, the instrument maybe. This is also referred to as case role analysis, thematic analysis, and shallow semantic parsing. Okay. So semantic parsing maps the natural language sentences to a logical form. Essentially what this is trying to do is get it to a form which is now a structured data, right? We all know as computer scientists that we want things structured. Because once we have them structured, then we can do something with them. But until they're structured, we can't do anything with them, right? So one of the obvious things that we've talked about in terms of our planning lectures and other pieces is that we've used logic as one knowledge representation. So an example here would be to get this sentence into a logical form that we could then do some action. So in this example here is that basically we say how many cities are there, we take that in, we turn it into logic, and then that logic is used to inform a logic-based language, i.e. Prolog here, to then make a query which is then going to return that value about how many cities there are in the US, if that program knows it. So this is a way that there's that transformation from unstructured to completely structured, so that we can then operate on it. Okay? So textual entailment is determining whether one natural language sentence entails, implies another under an ordinary interpretation. So this is another semantic task. If you have a sentence, what does it entail? What does it mean about the different pieces? So there was a challenge. There's one of the things that as drives, I think, even the vision world, but also in NLP, is corpus, and corpora is the plural of that, which is basically these collections of text or speech that have usually been annotated and also have results of other algorithms that are applied there, so people can compare their algorithms. So one of those things was a challenge where they had this entailment corpora generated. It's called the Pascal challenge. Pascal does a number of different types of challenges. The idea was here is looking at these things, it's going to ask you, you get some text, and it's asked you a hypothesis, and the entailment is whether it's true or not. Okay? So for here, example here was, eyeing the huge market potential currently led by Google, Yahoo took over search company Overture Services Inc. last year. The hypothesis is Yahoo bought Overture, and the entailment is true. All right. Microsoft rival Sun Microsoft Systems Inc. bought Star Office last month and plans to boost its development as a web-based device running over the net on personal computers and internet appliances. The Microsoft bought Star Office? No. So the entailment here is false. So I won't go through the other ones, but the idea here, again, is that from whatever is written in here, we're trying to validate that we understood it by understanding these entailments. And so that's one of the ways that we're testing these things. Okay, so let's go on to the third task we talked about, which is pragmatics. So here there are a couple different things that often show up in pragmatics. One is anaphora, or resolution, or co-reference. And this is like determining which phrases in a document refer to the same underlying entity. So John put the carrot on the plate and ate it. So now we have to determine the reference for it, right? So it could go to the plate, it could go to the carrot, right? And given the context and because he ate it, it's obviously, hopefully going to be the carrot. Another one here is Bush started the war in Iraq, but the president needed the consent of Congress. So the president should go back to President Bush. All right. Another one here, and this one's a little bit difficult because if you look at this, what it's referring to, you want to get the right object. So today was Jack's birthday. Penny and Janet went to the store. They were going to get presents. Janet decided to get a knife. Don't do that, said Penny. Jack has a knife. He will make you take it back. So it, does it refer to that kite? No, it refers to that kite. the one that you got, not the one that he already has. So it's that distance from that, the distance makes it difficult, but it's also because we have two different words there, two different nouns. But we, as a human, we would understand that it meant the one that you bought, not the one that Jack has. All right. Okay. Now, another type of pragmatics is this ellipsis resolution, and that's what often when people speak, they leave out words. They don't need it in there, and we just understand them. But for machines, that's difficult. All right, for computers, that's difficult. So here we say, here's an example: wise men talk because they have something to say; fools because they have to say something. So what's left out of here is, well, what is fools talk, right? Because they have to say something. So here, the idea here is again that we somehow have to be able to infer what those words that are missing. And that's part of the task of doing these pragmatics and in ellipsis resolution. Okay. So now let's look at a couple of applications of what you might use NLP for, some additional tasks. Information retrieval is one. This is sort of you don't have to have a deep understanding of a sentence. So typically you can do find documents. The goal is to find documents on the web, say, that are relevant to a user's need for information, some query. Using statistical information about the words in the text and or links to the text from other pages to rank relevancy. So you find a set of pages that you think apply, and then you're going to try to rank them some way. And we all, believe it or not, I mean, to you guys, this is obvious as breathing. But in the 1990s, when I was in grad school, this didn't really exist. It was in its infancy. So this was something new. There are algorithms. The simple ones are the kind of Boolean key models, terms and documents. Do those terms show up in the documents? No ranking really occurs there, but it's a way of finding out a set of documents that apply. And then you can do some kind of ranking relevancy using a scoring function. Example is the BM25 scoring function that usually has different terms. I'm not going to go into details of that, but it's often about how frequent a term appears in a document. And the problem with that, obviously, is that people have gamed the system and they start using tons and tons of those words to bring that up to the top of the search, right? And so then there are other ones like Google came up with in the late 90s, the PageRank, which is this idea of looking at of the relevant documents. You also look at the ones that are documents that are linking to that document, and then look at the credibility of those documents in order to assess the credibility of this document, and that goes into the ranking. So that way you can try to rule out people just gaming the system. Hits was another one, which is an improved version of that in some sense. Okay, information abstraction. This is where you try to identify phrases and languages that refer to specific types of entities in relation to the text. The idea here is that you're looking at documents and you have a particular take on it that you want to understand certain information about it, fill in roles. There was a competition in the again the late 90s that was I think indicative of this kind of information extraction. It was called the MUC competition, and in the MUC message understanding, I can't remember what C stands for, competition probably. So the idea here was they had a corpus of different examples that they could train on and corpus that they would test on, but they were all about documents that may or may not talk about terrorist activities. So they were like news reports. And the idea is you'd have these kind of templates that they draw up, and they would try to look through all the text and free-flowing text and try to match up fillers. Oh, that's the terrorist in this role. That's the weapon of choice. That's the location. And you try to fill out this template. And so this information abstraction was for that specific need of trying to understand terrorist activity. So that was an example of it, of the competition. We do lots of different pieces here. Again, it's trying to match what the kind of the things that you're looking for in the free-flowing text. So in this example, Michael Dell is the CEO of Dell Computer Corporation and lives in Austin, Texas. We're matching the people is Michael Dell, the organization is Dell Computer Company, and the places is in Austin, Texas. And so we're extracting that from the free-flowing data here. The relational extraction means that we're sort of getting the relations that Michael Dell lives in Austin, he's a CEO, and he has a Dell component. So that's a more sophisticated model of relationships among the objects that we've determined from the text. All right? Okay, question and answering. This is the idea that we all saw in the Watson, and we're going to hear much more, and I think it'll be kind of a good lecture, is the next class when Eric Nyberg comes to present on the Q&A technology in Watson. All right? So that'll be really interesting. So I'm not going to say too much about this, other than this is the idea of when a question is asked, and you can give some kind of response to it. Question and answering, right? And so you have to really understand what the question means. So when was Barack Obama born? August 4th, 1961. You had to understand that it was Barack Obama that we're talking about. You have to understand that you're asking for a date on which he was born. So you have to pick this up, all right? Who was president when Barack Obama was born? JFK. How many presidents have there been since Barack Obama was born? 9. So again, you have to really understand the sentence at some level in order to answer it. But we'll understand how deep that understanding is. I think we'll have a better sense of that when Eric starts talking about it. I think these are good questions to ask. All right? Okay. Text summarization is another kind of task that could be done. Produce a short summary of a longer document or article. Given this long text here about Barack Obama winning the Democratic nomination in 2008, over Hillary Clinton, looking for some kind of short summary of that. Senator Barack Obama was declared the presumptive Democratic presidential nominee. So in order to do that, you have to have a kind of a deeper understanding of these plays, play the roles. Usually there's some notion of what the summary is supposed to include, and then we're trying to extract this down into a shorter summary. So again, these are all the different kind of tasks that NLP can be used to try to solve. Okay, so machine translation is another one. Translating one sentence in a language to another sentence. So, hasta la vista, baby, until we see each other again, baby. All right? That would be the kind of notion. One of the things that comes up in this machine translation is that ambiguity resolution is quite difficult, because as you translate across languages, it gets pretty large. A lot of ambiguity. It gets sort of the vulnerability of it. The syntactic and semantic ambiguities must be properly resolved for correct translation. So you say John plays the guitar, John toca la guitarra, means we're using toca here for plays, because we're playing an instrument. Okay? But here, John plays soccer, it's a different word in Spanish, juega. John juega el fútbol. So you have to know when you're switching to language. In English, it's the same word, but when you're going to the other language, they're two different words because they have two different senses. So this is an example of when things go awry and you don't get it right. So this is basically translating to English, from English to Russian, and then back to English. And you can see, it's like the game of like telephone, right? And you see how bad it gets. Well, this gets pretty bad here, right? So the spirit is willing, but the flesh is weak. The liquor is good, but the meat is spoiled, right? Out of sight, out of mind, invisible idiot. Okay, so you can see that that ambiguity gets amplified as you go across these things. Okay, so some ways to resolve the ambiguity is choosing the correct interpretation of linguistic utterances requires knowledge of the syntax. An agent is typically the subject of the verb, the semantics. Michael Nelling are names of people. Austin's is the name of a city. Toyota is the car, a Prius. Okay. Pragmatics, context of the thing. World knowledge. Credit cards require users to pay financial interest. Agents must be animate, and a hammer is not animate. Right. So these are all the kinds of things that you have to bring in order to understand these different things. And you have to do each one of these steps in order to try to distinguish it. The thing about it is that if you do each one of these steps in order, there's no guarantee that you'll get it, because you probably have to go back and retry things based on conclusions you come from the other steps. Okay, so automatic knowledge acquisition. So in here, manual knowledge acquisition is what has been done prior to using statistical and machine learning methods for acquiring models for corpus of English, of language. So they used to have these traditional rationalist approaches to language where processing required human specialists to specify and formulate the required knowledge. They'd go and make painstaking rules, that they would generate and craft themselves. The language would have numerous exceptions and irregularities, and it would only apply to usually some very narrowly scoped set of problems that you'd want. So it's very narrowly scoped, not a general approach at all, and you couldn't do it for big pieces. So manually developed systems were expensive to develop, and their abilities were limited, brittle, not robust. Couldn't extend out to more general approaches. Naturally, NLP researchers all were looking for more general methods to apply to this. So they started looking at these things, these automatic learning approaches, to use machine learning methods to automatically acquire the required knowledge from appropriately annotated text corpora. All right? So various referred to as corpus-based statistical or empirical approach. They were first used in the 1970s, just tried, and into the 80s and 90s they became dominant. In fact, they almost all research tends to use these techniques now. During the 1990s, statistical training approach, as I said, became dominant. Just to give you a sense of that, if you look at this, it starts off very little, but by 2001, it's covering almost everything as using those kind of techniques. All right? Okay, so the learning approach is you take these manually annotated corpora to give you some kind of baseline. You take the machine learning and you run your algorithms over it, and you create some kind of linguistic model or knowledge from that corpora. And then you take some new raw text and you run it, use this knowledge to empower the NLP system you've done, and you run it through there, and sure enough, you get your automatically annotated text. And there's some level of precision and recall in which this may or may not be right. All right? The better you go, the better those values will be. Okay. So the advantages of the learning approach is that a large amount of electronic text are now available. The electronic format and sharing of that makes it much easier. It used to be very difficult to get corpora. Annotating the corpora is easier and requires less expertise than manual knowledge engineering. Now that we have these automatic means, huge parts of it can be done through these automatic means of annotating the text based on previous performances of those algorithms. Learning the algorithms have progressed to be able to handle large amounts of data and produce accurate probabilistic knowledge. And the probabilistic knowledge required allows robust processing that handles linguistic regularities as well as exceptions. All right? So it's a very powerful means of getting these models without having to painstakingly hand code each thing in the corpora about saying, oh, that's a determiner, that's that expression, that's what these things mean. All right? Okay, so the importance of probability. Unlike interpretations of words, it can combine to generate spurious ambiguity. This is a valid sentence, believe it or not, in terms of, but it has no meaning. This is, again, has 4 parsers, here, including the meaning of the insects of a variety called time flies are fond of a particular arrow, a command to record insect speed in a manner that an arrow would. Some combinations of words are likely, more likely than others, so that if you have Vice President Gore, it's more likely than Dice President Core, right? So these methods allow you to assign probabilities to what's more likely, and it helps you to disambiguate by taking the more probable ones for that language. Okay? And that's a way of resolving the uncertainty that you might have in the ambiguity. Okay. Human language acquisition. Humans, I'm not going to go a lot into this because I want to get ahead a little bit, but basically this idea of you have this model of how humans might learn things, and then we have a model of how we're doing things here through these statistical means. And there's a question about whether those things are the same or not. Your intuition feels like, you don't know whether you're, capable of being this rapid statistical evaluator, and that you have these statistical models in your head that you just have compiled down to some other form. There's lots of debate about these different things. So I think a lot of people suspend that question and just look for the results and look more for the end result and say, is this an effective way of working, and not whether it's epistemologically accurate to humans. Okay? This is just the problem that I was pointing out earlier, that if you do things in strict order of syntax, semantics, pragmatics, you may get in trouble. And here's an example of that, is that you see this thing down here. At the zoo, several men were showing a group of students various types of flying animals. Suddenly, one of the students hit the man with a bat. And the question is did he hit the man with a bat, or did he hit the man who had a bat, who was holding the bat, right? And so you don't know how to disambiguate that. And in this example here, if a hard decision is made at each stage, cannot backtrack when a later stage indicates it's incorrect. So if you attach in the syntactic phrase with a bat to the verb hit, right, you're not able to go back to realize, oh, maybe I should attach that to man, the man with the bat, not hit with a bat. All right. So if you did in the stovepipe way, you wouldn't be able to go back. So what do you do? One of the ways that you might look at this thing is to try to do this in a more integrated way. You could have multiple interpretations of the sentences going at a time instead of a single probable one. Maintain all these different ones that are possible, and then pick out the one that has the highest probability. But the problem is that there could be exponential number of meanings, and it's hard to manage all those things. You do try to get better at it by having some kind of better data structures, word lattices, compact forests, parse trees. But the point here is that it's still hard to manage. Another way to try to do this is to try to do this in some kind of integrated approach where you don't stovepipe and you try to bounce back and forth between all these different things. In a way, that was more like what you saw when we talked a little bit about hearsay 2 and the speech understanding system back when we were talking about blackboards. But this, again, is difficult to design and implement, and it's potentially computationally complex. So not a lot of significant work. I mean, people are working on this problem, but no huge breakthroughs yet. Okay, I'm not going to go through too much of the history here because I want to get a little bit to the Engrams. The history here basically is that they start off with these sort of context-free grammars, these finite state transducers to try to understand language and do this OCR. And then in the 60s, we remember when Zico told you about ELIZA, and we had these algorithms that you typically use, at that point I think we were using like matching by Winston to fill in roles and plays, particularly structured, not general. If you talk to ELIZA for any more than like a minute, it would drive you crazy because you'd realize what was going on. All right. Semantic networking models of language. They started to have this notion of, especially coming out of MIT, was a notion of what they called the autonomy of syntax, where they didn't want to look at semantics, and they simply said that everything could be gotten from syntax. And so they created these different networks. One of them was called an augmented transition net, and they're very cool if you ever want to get something to work on a very limited domain, but they're not generalizable. And then we started to look at these Bayesian methods early on for identifying authorship, and this was sort of the beginning of the statistical approaches to things. Shrewdloo was that block scroll program by Terry Winograd. The point here was that he also had this natural language interface to allow you to say, move that block over here, or put that block over there, or get this kind of configuration. And it was all about trying to understand how to do that. It, again, had limitations on what it could do. He came out of that MIT autonomy of syntax type of approach. Roger Schenck came out of Yale, and he created this whole school and lots of progeny where they took a very different approach, which they used these things called conceptual dependencies, and they talked about primitive actions. Again, this was all about trying to develop some kind of understanding from a non-syntactic, but more of a semantic approach. Again, they moved into a lot of the case-based reasoning areas and into these kind of understanding summarizations of stories and story generation. And there are different kinds of parsings that came out where we started again to use statistical ways to try to understand speech understanding and language. Finally, in the 80s, we really started to move to the statistical methods for doing syntactic analysis and position taggings. And in the 90s, it kicked off. Almost everything came out of this. There were some of the parsers were moving, the word sense disambiguation, information abstraction, all these things started to really take off with these kind of introduction of the robust statistical parsers. All right? And in the 2000s, we really continued on with this kind of statistical and machine learning hybrids that work together to automatically generate these things. And they've become a much more general method than was done prior to these kind of methods, which were very hand-coded towards very particular domains. Okay, so let me go on here. So now let me go to this language models and Engrams. So here now I'm finally going to go to a particular example of one method that has been used with a fairly simple method that's been used with a lot of success on different kinds of things like information retrieval, some on information extraction. So we'll talk about this piece right here. So the idea here is that we have formal grammar rules that are very brittle in the sense that if you match a regular expression or if you match this formal grammar, you're part of that language model. But if you don't match it, then you're out, and there's no ability to withstand noise. All right. So then this other idea is to have this kind of probabilistic commandment of a language that gives you the probability of giving an input, whether it is part of that language or not. It can be generated in that language. And to specify a correct probability distribution, the probability of all the sentences in a language must sum up to 1. So basically, what you're coming up with is this probability that a language will be part of this language model. All right. So here's a quick little thing. We have speech recognition. I ate a cherry is a more likely sentence than I ate Jerry. And so the idea here is that if you have the right language model and the right probability, this will give you a higher probability for this set of characters and strings and words than you would get for the other one. Same thing with here. If you have a higher probability of one thing being correct than the other, then maybe your OCR will be more accurate, right? Machine translation, again, you're trying to do the disambiguation by saying, I'm going to take the one that's more probable. In this language, this is a more probable occurrence, and therefore, I'm going to disambiguate based on that probability. Generation, I'm going to generate sentences that look more like sentences I've seen before, and context, sensitive spelling correction. As we all know, when we use our phones and get irritated that it gets the wrong words, but often it does get the right words. A lot of it has to do with this notion of being able to contextualize it and pick the one that's more probable. All right. Okay. One other task that can also be done with this probability, if you have that in the language model, is that you can also do some kind of anticipation of how to do completion. So please turn off your cell, and like with, might be 60% of chance that phone is the next word there. That's the highest probable word, and therefore phone would fit there, and that gives you a better completion of those sentences. So this also allows you to do predictive text input system to guess what you're typing and try to anticipate and help you type that. Okay, so now let me talk about the specific method that we're talking about, which is called the Engram models. They estimate the probability of each word. They can do it also for characters, but I'm not going to talk about that. I'm going to talk about it in terms of words. Okay, estimated probability of each word given prior content. So what's the probability of this phone given that you see these texts prior to it? Please turn off your cell. All right. So an Engram model uses only n-1 words of prior content. A unigram just has the word. A bigram has one of the prior content, and trigram has two of the prior content. All right. And naturally, this is going to use this kind of Markov assumption that we've seen before, and depending on which one you use, it will depend on which K order of the Markov it will be using. Okay, so problems with there are some problems, right? With, you see this corpora, and what's some of the problems of just counting the words in there? How many? Because you're looking for frequencies. How often those words occur in the context of those windows prior to the other words you're trying to predict. So, okay, so one of the problems with counting words is how many words are in the sentence. It depends on whether or not we treat punctuation marks as words, right? So, important for many NLP tasks, grammar checking, spelling error, they need to know about punctuation. So, it depends on what you're doing. Spoken language corpora utterances don't usually have punctuation, but they do have other phenomena that we might or might not want to treat as words. You put things like in there to do connectors, fragments, filled pauses. Do we count them as words? How do we break them down? So this is just problems of kind of breaking down the language so that you can then apply the Engrams to it. Some more of them is capitalization. Should they and they be treated the same with a capital T and lowercase t? Are they different? Are they the same word? For most statistical NLP, they are treated as the same. They do something that often we call stemming, which is try to get rid of also prefixes and postfix, suffixes of them. Sometimes capitalization information is maintained as a feature. Inflected forms, should walks and walk be treated as the same word? For Engram, they're not usually used as the same word, but in other contexts you might think of them as the same word. It's based on the word from, that is how they appear in the corpus, or rather the lemma, that is the set of words, the lexical forms that have the same stem. So walk and walk in this case would be the same stem, and in which case they would have been the same. All right. So problems with counting words, you need to distinguish word types from word tokens. So if an example is here's an example sentence, all for one and one for all. So that has 8 tokens, 1, 2, 3, 4, 5, 6, 7, 8, counting the period. All right. But there are 6 types, assuming capitalized and uncapitalized version of the same token are treated separately. All right, so it depends on how you're going to keep track of these things between the types and the tokens. All right, so here's sort of how to generate the probabilities for the engrams here. Here's a definition for a word sequence. A word sequence is a sequence of words from 1 to n here. As we've seen before in the chain rule of probability here, but the probability of that sequence of words is the probability of the word 1 times the probability of word 2 given word 1 times the probability of word 3 given word 1 and 2, that the sequence of word 1 and 2, and so on until you get the rest. That would be the probability for that string. Okay, but when we do bigrams or n-gram approximations, we limit how far back we look. All right, instead of looking at the entire length of the string, we look back either 2 or 1 or exactly. All right. Okay, so estimating the probabilities. So to get those probabilities, we use it by looking at the counts in that corpus that we looked at, that we generated the values from. The n-gram conditional probabilities can be estimated from the raw text, or the corpus, based on the relative frequencies of the word sequences. And so the relative frequencies are computed this way. There are other ways that you could do this. This is just one of the computations. There are, in fact, other methods that perform better. And here, which is that given the string, what's the probability of this string? Given n minus 1 of that string, it's the count that you see of, with that, the precessor plus n, I'm sorry, the probability of word n minus 1, the word prior to it, given that you see both the word and the word prior to it over how many times you see what's prior to it. All right, so that gives you some ratio of how often you see that, relative frequency. This is just a generalization of that, all right, for n. If it's, instead of 2, it could be 3, 4, whatever. To have a consistent probabilistic matter, this is just about how to treat sentences in order to talk about where the beginning of the sentence or the end of the sentence is, or the beginning of the corpus is, or the end of the corpus is. You can annotate additional things by adding s. Beginning of sentence and end of sentence is /s, and that way you can say, you can start asking questions about what's the probability of this starting a sentence, for example. All right, so you can think of these language models that get represented by the n-grams as also a way to, you could sample them to generate sentences too. So you could say, starting with that s character, what's the probability of seeing of the next one, draw from that distribution, get a word, and now s in that word, what's the probability, given your n-gram probabilities, of the next word, and draw from that distribution. And you can generate a bunch of sentences, and then a sentence would end with a /s, and that'd be the probability, you can get that. The other thing that you can do is you can figure out this basically what this is just saying is that using those kind of relative frequency estimates can be proven that it'll give you a maximum likelihood estimate, so the statistical maximum likelihood estimates, such that it will predict that that these will guarantee that it will predict the model the corpus T given that model. Okay, so one of the things you can do is compute the probability of a sentence given that model. Right? So the way you can do that is you can simply break down these pieces into their individual pieces here, and then look up the probabilities that you've calculated from your corpus, and you can go ahead and multiply them out, and you can see that. So this is all taken from this Berkeley restaurant project, which was a way they would ask people what they want, and these are different ways that you could get that inputs from that. Here's one for if you get English food or for Chinese food. Notice that this one has a more highly probability. More people asked about Chinese food than than for English food, probably for good reason. Okay, so let me go on here. So the model here is that you train on a corpus, as I've said before, and then you test on a different one. You don't ever test on the one that you train, okay, because that's not fair. So a language model must be trained on a large corpus of text to estimate good parameter values. Model can be evaluated based on its ability to predict a high probability for a disjoint held-out test corpus. Testing on a training corpus would give an optimistically biased estimate, obviously, because you've trained on that. Although it's not always perfect, that's for sure. Ideally, the training and test corpus should represent something of the actual application data. This is a little bit hard because often the application data that you work on, it's hard to get a big corpus that's that. So you use more general corpus, and then you try to kind of weight it more specifically by taking a smaller one that's the domain-specific one that you're trying to do your application for, and weight that general corpus by this one in order to change those values. And so you get sort of the general pieces, but then you've weighted it to the specific by the small one, because it's hard to get a big corpus for a specific domain. All right, so one of the problems that comes up here is that there are unknown words. You know, just because you train it on some corpus doesn't mean that you're going to have any idea that you know, there might be many occasions, in particular because we're talking about words, where there might be groups of words together that simply won't show up, or there'll be a word that won't be in the corpus that will show up in the test. So what do you do with the case, the out of vocabulary words? Well, you train a model that includes an explicit symbol for an unknown word, and usually they use this to market the unknown word, and then basically you're trying to figure out some probability for that unknown. And there's two ways that are sometimes used with that. One is to choose a vocabulary in advance. You set the vocabulary in a sense, and then everything else is said to fall into the category of unknown, and you just assign the probability based on everything else being unknown. The other one is to replace the first occurrence of each word in the training set with unknown. So you're going through the corpus, you see a word for the first time, and you go ahead and say, the first time I'm just going to assume that that's unknown. Every time I see a word for the first time, I assume that's an unknown. The rest of the times I'm going to go ahead and count it as I would normally count it next time I see this word. And that would create some kind of probability for the unknown here. You can also improve the resolution by having classes of words, so that you could have, like, words that are all digits or email address, and then you could have separate unknowns for each one. So instead of having one unknown represent all these words, you can kind of subdivide it into smaller ones and have more accurate probabilities for the specialized ones. Okay, so in evaluation of the language, basically all this is saying is that it's better to do it. It is better to do it in the real thing, right? In the real problem, in the real place, but that's often hard. So you often do it on these corpuses that are cheaper and easier to get to, and then you're trying to, at some point, circle back and see if you can apply it to some one realistic set of data. So one of the things that you have is you have these models, and you want to understand how well the model fits the test data. So given some test data, you want to say, how good is it at predicting? How good is it going to be able to assign a value to that? If you think of it this way, if you think that as you do some test data and you have a huge number of choices at each step you're going, then you're thinking, maybe I don't have a very good predictor for this test data. But if you have a fairly tight, not a large branching factor each one of those cases, then you might have a better predictor. So use probability models that assigns to the test corpus. So normalizes for the number of words in the test corpus and takes the inverse. This is something that's called perplexity. And basically, this is going to measure the weighted average branching factor in predicting the next word. Lower is better. So the better that you can have this, the lower this value is, the lower your branching values are, and the better you can predict, more likely that you're going to predict for that test value. Okay, so example perplexity evaluations. Models trained on 38 million words from the Wall Street Journal using 19,979 word vocabulary, evaluate a disjoint of 1.5 Wall Street Journal words. For a unigram, didn't have great prediction, 962 is it. Bigram is 170, the trigram is 109. So as you can see, as n gets bigger from 1 to 3, you get better results in terms of being able to predict these things. All right? Okay. So another effect that happens is that since there are any number of combinations of words, not just individual words, but combinations of words that can show up. You can always come up with some, often you'll see in our test suite, unique sets of words that didn't show up at all in when you're creating your Engrams from the training set. And therefore, you have kind of the sparse data problem, right? You don't know, again, what values to assign to these things. So there are different ways and different methods for trying to assign values to these things that you haven't seen before, right? So you're going to try to do some approximation for what you haven't seen before. So if a new combination occurs during testing, it's given a probability of 0. If you don't do this kind of smoothing, if you get that 0 and you multiply all the zeros and that 0 out, and the probability of that sentence, it's going to be zeroed out. And so that's something they call infinite complexity. So what we do is we do some kind of smoothing or regularization of that. And when you do that, you're adding probability mass to an unseen event, so it requires you to take some mass away from something else, all right? Or discounting in order to maintain a joint distribution that sums to 1. All right, so one of the most common one was this Laplace add 1 smoothing. And the intuition behind this one is that basically if there's a Boolean x that equals false in all n observations you see of this, then in two more trials, one may be true and the other false. So again, here what the idea is, we're taking these counts and we're going to, no matter what this is, we're going to add 1 to it. And then we're going to divide it by the amount of times that you see it, plus v, which is the total number of the vocabulary base of that model. So by doing that, you essentially are going to give some value for things even if you haven't seen it. It's going to have some value. One of the problems is that the v here is often too much, and it gives too much mass to these unknown sequences of words. So frequently, instead of using v, you'll use some kind of discount factor here for delta that will discount that v value so that you don't have that huge overload. Some more advanced smoothing is that many advanced techniques have been developed to improve smoothing for languages. There's good Turing, interpolation, backoff, Nisi, class-based, clusters, Engrams. I'll go into just a couple of these things. Basically, what the notion often of these, a couple of these methods is this idea of saying, oh, okay, I want to use this really high n value, which is really good. But the problem is when I use a high n value, I often end up with more sparse data. I have more problems. I see more things I don't recognize. So what we do is this kind of iterative method of saying, hey, I'll do with the n one, but if I can't use the Ngram using the n of 3, then I'm going to try an Ngram of 2 in place of that, and then plan of 1, or some kind of summation of those things. And that way we can kind of fill back in the data with smaller informed Ngrams. So let me go for an example here. So in the interpolation here, we're looking at Ngram of some n size, and then we go for like a try to a bi to the single, to the unigram here. And we have some kind of weighting factors here that are basically just averaging, they have to add up to 1. All right? So that's one way to do it. Another way to do it is that if I have a value given at the trigram value, use that value. Right? That one before used all 3. If I have that one, use the best one. If I don't have one, then use the next best one, the next shorter one. So if it starts with 3, then I use 2, and then I'll use 1 if I don't have it. All right? So it's just a way of filling in that gap of that data. Okay? Okay. This is just talking about one of the things that because of your n window, you can be myopic in the sense that you have a horizon and that you won't see things far away. And so you might miss different things. So in this case, is something that matches with man, but there are many words in between those. So you don't get those relationships. All right? So it's always going to have some problems with those kinds of things. I'm not going to go into this. We don't have to do this because there's no time. So I'm just going to end with this Ngram summary, things that take away messages. So Ngrams allow you to make language models assign a probability that a sentence is a legal string in a language. They are useful as a component of many NLP systems, such as automatic sound recognition, optical character recognition, and machine translation. Simple Ngram models are easy to train on unsupervised corpora and can provide useful estimates of sentence likelihood. The maximum likelihood estimator gives inaccurate parameters for models trained on sparse data, right? You obviously need to have good data, and in order to address this is you try to use these smoothing techniques to adjust the parameter estimates to account for unseen but not impossible events. Okay, and looks like it's perfect timing here. All right, so if you guys take a look at the problem that set that was posted today. If you have questions, in particular for me, if you have questions about the scheduling problems, go ahead and email or sign me or do a Piazza, and I'll look to be proactive about that. Okay?